Okay, these are the topics we're going to cover in this lecture. Components of a wave. Wavelength is the linear distance covered before a wave starts to repeat itself. It is usually measured from crest to crest or trough to trough. A wave with a lower wavelength has a higher frequency as it repeats itself more times per second. In the visual spectrum, violet is considered to be a high frequency light and red is considered to be low frequency light. So here's the formula. The speed of light is a universal constant. It's always 3 times 10 to the 8 meters per second. Frequency is in seconds, or inverse seconds, as it's a measured cycles per second. Hertz sometimes used as the frequency, units for frequency. It doesn't matter, and sometimes you'll even see like per second like that. So the frequency is indirectly proportional to the wavelength, and because the speed of light is a constant. So as the frequency increases, the wavelength decreases, or vice versa. The frequency decreases, the wavelength increases. So we want to find the frequency of a green light that has a wavelength of 545 nanometers. So here's the equation. You can rearrange it to find the variable you want, or just plug it in. And plug your numbers in, and then make sure you're careful because they gave us the wavelength in nanometers, but the speed of light is in meters per second, so make sure you convert, and then you should get 5.5 times 10 to the 14th hertz. So as wavelength increases, frequency decreases. The visual spectrum of light, which comes from white light, can be divided into all the colors of the rainbow. So indigo light has a wavelength about 400 nanometers, and red light has a wavelength of 750 nanometers. If the wavelength exceeds 750 nanometers, it falls outside the visual spectrum. However, it's still considered electromagnetic radiation, right? The rainbow represents a continuous spectrum. It's continuous because there's no breaks in color. One color just kind of fades into the next, as every wavelength of light between 400 and 750 nanometers is there. All right, so quantum theory and Planck. Planck hypothesized that the energy radiated from a heated object like a stove or a light bulb is emitted in discrete units called quanta. So in the macro world, we assume that energy increases in a continuous stream, like light, but it doesn't. When we add heat to a pot of water, it slowly gets warmer, right? But in the micro world, that straight line is actually a series of tiny little steps. So in each step is one quantum of energy. Energy can't increase by a fraction of a quantum. It either increases by a whole quantum or it doesn't increase at all. So here the quantum depends on a specific frequency of electromagnetic radiation. So with this equation, you can find the energy per quantum from the frequency or vice versa. As frequency increases, the energy per quantum increases. So in each of the quanta in a high frequency light, like violet light, contains more energy in the quanta in a low frequency, like red light. All right, the photoelectric effect. So here the ejected electrons complete the circuit. The metal plates act as a parallel plate capacitor when they're hooked up to a potential difference. Electrons are pulled out of the collector plate, causing the plate to develop a net positive charge. Electrons build up on the metal plate that the light shines on, giving a net negative charge. So if the frequency of light hits the surface of the metal, it will, the correct frequency of light hits the surface of the metal plate, it will eject electrons. So those electrons are then drawn toward the positively charged collector plate, and the flow of electrons complete the circuit and causes the bulb, or whatever, to light up. So here are just 4 facts. The first fact, high-intense, low-frequency light does not eject electrons, even if it shines on the surface for several days. Intuitively, this doesn't really make sense, right? If you put a pot of water on a stove set at medium heat, it will boil eventually, right? It boils quicker if you set the stove to its maximum heat, but the water will eventually boil at lower settings. Energy is being added to this system, so one would assume that an electron would be ejected when enough energy has absorbed. But that never happens. Second fact, when the threshold frequency is reached, electrons are ejected immediately. Again, you would think this doesn't make sense, right? So if we wanted to, suppose the threshold frequency is 5.51 times 10 to the 14th hertz. You could shine light with a frequency of 5.50 times 10 to the 14th hertz on the metal plate for days. but no electrons are going to be ejected. As soon as you change that frequency to the threshold frequency, electrons immediately eject. So one would assume that energy needs to be absorbed for some period of time, but it doesn't. All right, increasing the intensity of a light at a frequency that will cause electron to eject results in a higher ejection rate. But all ejected electrons share the same velocity. So again, you'd think that shining more light with a frequency of 5.1 times 10 to the 14 hertz, so I'm just making up, will cause the electrons to eject with higher velocity as more light waves are hitting the surface, but it doesn't. It does result, though, in a higher ejection rate. And the fourth fact, increasing the frequency of light causes electrons to eject with a higher velocity. So as we know from Planck, increasing the frequency increases the energy per quantum. Okay, so then we get Einstein. And so this is what we know. We know electrons don't eject until the threshold frequency is reached, even after prolonged exposure, right? So this would lead us to believe that there's a one-to-one relationship between an electron and another particle. If it was not a one-to-one, the electron would slowly absorb enough energy to break free from the metal surface. Okay, we also know once the threshold frequency is reached, ejections take place immediately. Okay, this further supports the idea that an electron absorbs a single particle containing a set quantity of energy. If they slowly absorb continuous energy, the ejections would not take place immediately. We also know at a set frequency, the velocity of all ejections are the same, right? But increasing the frequency increases the velocity of ejections. So this further supports the one-to-one relationship of electron to photon. So for there to be a one-to-one relationship, photons must be particles. And so that's what Einstein said. He coined the term photon. So now we know light is a particle too. All right, so the quantum of Planck is actually a photon. So this is going to be energy per photon now. So with this equation, you can find the energy per photon from the frequency or vice versa. And then as frequency increases, the energy per photon increases. So each of the photons in high-frequency light, like violet light, contain more energy in the photons in low-frequency light, like red light. All right, Bohr. Y'all seen the Bohr model before. Forces of attraction between electrons and the nucleus result from opposite charges, right? Electrons are negative, protons are positive. All right, this is Coulomb's law, and y'all need to make sure you know Coulomb's law because every time you need to justify your answer, more than likely you're going to use Coulomb's law to do it. So F is force of attraction, K is a constant, and then Q is your magnitude, your charges, like protons or electrons, and then D is the distance between the charged particles. Okay, if energy is added to an atom, an electron can move from a lower energy orbit, which is closer to the nucleus and more stable because the force of attraction is greater due to Coulomb's law. They can move to a higher energy orbit, which is further away from the nucleus and less stable as the force of attraction is less due to Coulomb's law. But it can only circulate around the nucleus in a quantized orbit. So Bohr labeled these orbits. N equals 1, that's the first shell. N equals 2 is the second shell. N is 3 is the third shell, blah, 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 blah. Okay? So these integers, quantum numbers, as the orbit, each orbit was associated with a quantized energy level. And he created this equation that could predict the energy of an electron in each possible orbit for the hydrogen atom, but it didn't work with multi-electron atoms. And we'll talk about that later in the next unit. All right, the shielding effect. So the electrons that are further from the nucleus are shielded by the inner core electrons. And the shielding effect reduces electrostatic attractions between the outer electrons and the nucleus. So this description is kind of incomplete, and we'll talk about it later in the lecture. But we know forces of attraction between charged particles decrease as distance increases according to Coulomb's law. The shielding effect further reduces this force of attraction on outer electrons. The shielding effect can also be explained through Coulomb's law as the inner core electrons are exerting a repulsive force on the outer valence electrons. So the names ionization energy, and ionization potential are interchangeable. The fact that energy must always be added to remove an electron means that this is an endothermic process. If all ionization potentials have positive values, right? So it's endothermic. If the energy was released, the value would be negative. Okay, this is first ionization atom energy data for a few elements, and this data tells us two things. First, it tells us that ionization energy decreases when moving down a group in the periodic table, and the second thing it tells us is that it increases when moving from left to right across the periodic table, just like this. Now, let's remember this from pre-AP. We labeled this, right? Okay. So Coulomb's law describes a force, not energy. Coulomb's law can be used to derive the electrostatic equation, which y'all don't need to know, is this. Okay. However, in both equations, force or energy increases as charges increase and distance decreases. Because the magnitude of the positive charge in the nucleus of helium is about twice that of hydrogen, the force required to remove an electron from helium is about 2 times that of hydrogen. So the 2 electrons in helium are about the same distance from the nucleus as the electron in hydrogen. So if the ionization energy of lithium is half as large as the ionization energy of hydrogen, if the most loosely held electron in lithium was about the same distance from the nucleus as those in hydrogen and helium, we would expect the ionization energy of lithium to be about 3 times greater, right? The most loosely held electron in lithium must be much further away from the nucleus than that in hydrogen and helium. So the shell model. If we look at the shell model, we look at ionization data. In this model, electrons move in 3D shells. Each shell is an exact set distance from the nucleus. So electrons that remain in a given shell of a neutral atom are always the same distance from the nucleus. It requires much less energy to remove the most loosely held electron, the valence electron, from lithium because it's much further from the nucleus than in hydrogen and helium. So in the N equals 1 shell, the first shell, it can hold up to 2 electrons. Moving left to right across the second period, 8 electrons can be added to the N equals 2 shell. So the second shell can hold up to 8 electrons. Moving from left to right across the third period, 8 electrons can be added to the third shell. We know that the third shell can hold 18 electrons right now, but we'll talk about that later. Okay, so there's a problem here. The first ionization energy for the third element, boron, in the second row of the periodic table is less than that of the second element, beryllium, right? We said it increases as you move from left to right. So why is boron energy less than that of beryllium? It happens with aluminum too. Its first ionization energy is less than that of magnesium. So we need a different way to analyze data. Okay. So again, 2 in the second, 8 in the third, 2 in the first, 8 in the second, 8 in the third, right? Okay. And keep in mind, these are the inner core electrons, and the valence one are on the outer shell. Okay. So photon electron spectroscopy, I'm going to explain how they gather this data. So the electrons that are ejected with higher velocities will experience less acceleration towards the positive plate in the magnetic field. The location where the electrons strike in the electrostatic analyzer is used to determine its velocity. So the kinetic energy of the electron can then be calculated using this equation. Only 1 electron is removed from each atom, but that electron can come from any shell. Removing a second electron from an atom wouldn't give us any useful data because removing a second electron always is going to require more energy than removing the first. So when the photon absorbs the electron, it's provided with the energy required to be ejected from the atom, ionization energy, and the kinetic energy associated with its translational velocity after it's left the atom. So the ionization energy for each ejected electron can be calculated by subtracting the kinetic energy of the ejected electron from the energy contained by the photon. So that's how they calculate it, okay? So here is PES data from 5 different elements. Usually when y'all look at this for practice problems and stuff, you'll have one spectra and you'll only have one atom on here, one type of element on here, but I wanted y'all to see it all at once. Okay, so the ionization energy on these graphs increases from left to right. The height of the peaks correspond to the number of electrons within that ionization energy. So hydrogen only has one peak, and it's half as tall as the helium peak because it only has one electron. Hydrogen has 2 electrons, so its peak has to be twice as tall. Lithium has 2 electrons in the first shell and 1 in the second shell. So the peak for n equals 1 is twice as tall as the peak for n equals 2. The ionization energy for the electron in the second shell is much less because it's shielded from the nucleus by those, it's further from the nucleus and shielded by those inner core electrons. Beryllium has 2 electrons in the first shell and 2 electrons in the second shell. So if you notice that the ionization energies for the electrons in the first and second shell increase as more protons are added to the nucleus. This can be explained through Coulomb's law, because Q in the numerator of the equation increases each time a proton is added. So now let's look at boron. We've got 3 peaks here. From our data from the first ionization energies, we assumed that the second shell could hold up to 8 electrons, and so they would have the same ionization energies because they're the same distance from the nucleus. But this data tells us the shell model needs to be revised because the second shell has to contain subshells with different ionization energies. So this is why the first ionization energy of boron is slightly less than beryllium, and the same thing with aluminum and magnesium. The same trend can be seen in the elements carbon, nitrogen, oxygen, fluorine. They'll have 3 peaks, which indicate that there are 2 subshells within the n equals 2 shell. So we can see that the first and second peaks indicate the presence of 2 electrons. For carbon, the third peak has 2 electrons. For nitrogen, the third peak has 3. For oxygen, it's got 4. And for fluorine, it has 5. And neon has 6. So the heights of the peaks are proportional to the number of electrons. So now this data tells us that the first shell can hold up to 2 electrons. The first subshell in the second shell can hold 2 electrons. And the second subshell can hold up to 6 electrons. So here's our revised shell model. The first can contain 1 subshell, right? 1s. The second shell contains 2 subshells, S and P. The 3 has 3 subshells, S, P, D. So sodium has 4 peaks in the photoelectron spectrum, electrons from 1s, 2s, 2p, and 3s subshells. Magnesium also has 4 peaks, electrons from 1s, 2s, 2p, and 3s. If we had PES graph, for the 4th peak of magnesium, it would be twice as tall of that as sodium because it contains 2 electrons. Aluminum to argon have 5 peaks, electrons from 1s, 2s, 2p, 3s, 3p. Potassium and calcium have 6 peaks, which are electrons from 1s, 2s, 2p, 3s, 3p, 4s. Scandium has 7 peaks. Evidence from other forms of spectroscopy suggests that the last electron in scandium is in n equals 3, not n equals 4. So this last electron falls into the 3D subshell. So we have a shielding effect within a shell. Electrons from 2s spend most of their time further from the nucleus than those in 2p, but the electrons in 2s have a higher probability of spending more time in very close proximity to the nucleus than those in 2p. Because of this, the overall shielding effect, which is caused by the 1s electrons, is greater for the 2p electrons than it is for the 2s electrons. The average distance between the nucleus and the electrons decrease as subshells within a shell are added. In other words, the average distance between the nucleus and a 3s electron is greater than the average distance between the nucleus and a 3p electron. So this would lead us to believe that the ionization energy for a 3s electron would be less than that of a 3d electron in the same element, Coulomb's law, remember, but that's not the case. So electron density close to the nucleus decreases for each subsequent subshell. Say that 3 times fast. That is added to a shell. So the decreases in electron density close to the nucleus increases the shielding effect. So you get that electron-electron repulsion from the electrons in the first and second shell. The increase in the shielding effect has a greater impact on the force of attraction than Coulomb's law when we were looking at subshells in a shell. Okay. So again, from Coulomb's law, we would expect that the ionization energy for an electron in 3D would be greater than that for an electron in 3P, as the average distance between an electron in 3D and the nucleus is less and less than that for an electron in 3P. However, the ionization energy for an electron in 3D is less than that for an electron in 3P due to the shielding effect. All right, here are your homework problems. Try these. We'll check them in class.